Insulin is one of the most important hormones in endocrinology, and you should spend some serious time on this because it's not only high yield, its effects and regulation are actually pretty complex. But before starting with the nitty-gritty biochemical mechanisms, I want to start by going over what I consider to be the core of endocrinology, the cause and effect of homeostasis. So to really generalize, what's the purpose of insulin? The purpose of insulin is to coordinate the body's resources during times when glucose is plentiful, primarily through anabolism, or building up complex molecules. Well, how does it do that? Well, the most intuitive way the body deals with a surplus of glucose is to store it, and that job goes primarily to our three reliable friends: the skeletal muscle, the liver, and the adipose tissue. When glucose is plentiful, insulin causes skeletal muscle to import and metabolize more glucose and store it as glycogen. The process is similar for adipocytes, but logically, fatty acid and triglyceride synthesis is the primary means of storage. The liver's a little different. Insulin actually has no power to control the transport of glucose into the liver, but it does cause increased glucose metabolism. But which does the liver preferentially synthesize? Glycogen or fatty acids? Preferentially, the answer is glycogen, but the liver's glycogen tanks fill up pretty quickly. When the storage capacity has been reached, fatty acid synthesis becomes pretty important because the liver can always count on the adipocytes to help with the storage. And the net adipocyte capacity is way bigger than the liver's capacity to store energy. The liver just has to package the fatty acids up as triglycerides and send them off with a VLDL postmark. Finally, insulin has a couple of important effects on all cells, not just the trifecta above. If insulin is an anabolic hormone, what would you expect its effects to be on protein metabolism? Insulin causes increased amino acid uptake and protein synthesis in all cells, while inhibiting proteolysis, which makes sense since protein synthesis takes a ton of ATP that's only really found when macronutrients are plentiful. And finally, for real this time, insulin increases the activity of the sodium-potassium pump, which may seem pretty trivial now, but it becomes pretty important in the treatment of hyperkalemia. Check this out in the renal section on potassium regulation. So hopefully that was a helpful demonstration of the big picture of insulin. Now I'm going to get into the mechanisms of how these regulations take place. Let's start with the secretion of insulin itself. This humble rectangle represents the beta cell, the place where it all begins. Before glucose even enters the picture, this tiny warrior cranks out granules of stored insulin day and night. The hormone is actually synthesized as a prohormone and packaged into vesicles. Now this is where the magic happens. Inside the vesicles, proinsulin is cleaved to form active insulin and the inactive C-peptide. These granules full of insulin and C-peptide park themselves right by the cell membrane, ready to be secreted at the drop of a hat. So the question of the day is, as always, why does anyone care? The real clinical value, and the one you'll be asked about on step 1, is C-peptide's ability to distinguish between different etiologies of hyperinsulinemia. Think about it. If you've got an insulinoma, you'll have high levels of both insulin and C-peptide in your blood. What about if you've just taken a mega overdose of regular subcutaneous insulin? I don't think so. Endogenous insulin is always accompanied by the co-release of C-peptide, but remember, exogenous insulin is never accompanied by C-peptide. How you get from high glucose to insulin release is a bit of a complicated song and dance that you unfortunately have to memorize for this test, but it's actually quite a bit easier when you see it animated than on paper. So, first of all, more glucose on the outside of the cell means more glucose transport into the beta cell, where it then gets catabolized to generate ATP. What follows is an inhibitory step where ATP actually deactivates an ATP-sensitive potassium leak channel. Without the leak channels working, K+ builds up on the inside of the cell, creating an increased positive charge that therefore depolarizes the beta cell. Now, this inhibitory step is always the hardest for me to remember, and unfortunately, it is an important one clinically as well. One of the major classes of diabetes medication, the sulfonylureas, increase endogenous insulin synthesis specifically by allosterically blocking these very same channels, in a way bypassing the glucose sensing step of insulin release. The depolarization of the cell opens everyone's favorite vesicle releasing channel, the voltage-gated calcium channel. Just like at an axon terminal, this allows calcium to enter and permit vesicle release. Now, this whole shenanigans is upregulated by a set of gut hormones called the incretins. They're discussed a lot more in the GI section, but the one you have to remember is GLP-1. When the cells in the GI tract sense sugar, they release GLP-1, increasing insulin synthesis by a variety of different mechanisms even before the sugar hits the bloodstream. That's why an oral glucose load will actually spike your insulin more than an IV bolus will. So now that we've taken a look at insulin release and regulation, let's see what it does when it's at its target. Insulin's actions are mediated via the intrinsic tyrosine kinase, or MAP kinase pathway. It's one of the more esoteric pathways, so I'll quickly take you through how it works. Insulin binds to an intrinsic tyrosine kinase receptor, giving each subunit the ability to add phosphate groups to the other. Once autophosphorylation takes place, a whole host of adapter proteins glom onto the activated receptor, the final result being the activation of two proteins, phosphoinositol 3 kinase that acts in the cytoplasm, and MAP kinase, which translocates to the nucleus to control gene expression. What does the signal cascade accomplish? As a matter of fact, everything you see right here. So now we're going to get into the cell-specific effects of insulin and how the different types of cells respond to insulin. We'll start with glucose transport. So remember how I said that insulin facilitates glucose transport in muscle and fat cells, but not the liver? The reason is, both myocytes and adipocytes possess vesicles containing the GLUT4 transporter. And insulin's P13K pathway causes the vesicles to integrate with the cell membrane, increasing the cell's ability to import glucose in the presence of insulin. In the case of striated muscle, the GLUT4 transporters can also be translocated to the membrane with exercise, which explains why exercise is so important for insulin-resistant diabetic patients. Can you think of a way this might go wrong? You're probably not used to thinking of exercise as a harmful thing, but this is actually a pretty common cause of hypoglycemia that you might see on step 1. Patients who take insulin are supposed to decrease their insulin dose before exercising to account for the dual drop in blood sugar. But when they forget, it can lead to some pretty significant hypoglycemia. So how does the liver get its glucose? We talked about the myocytes and adipocytes. What about the hepatocytes? Well, those use the GLUT2 transporter, a transporter that isn't controlled by insulin. Now, we're going to go into this transporter in some detail, and I know it's weird to spend so much time on a transporter that's not insulin dependent during the, insulin chapter, but this transporter is pretty unique. The first cool thing about it is that it's bidirectional. Glucose can either enter or exit the cell. Now, why is that so important for the liver? Because unlike other cells, the liver doesn't just want to suck up all the nutrients it can. As the major reservoir of glycogen for the body, it needs to be able to secrete glucose into the bloodstream when the body's in the fasting state. GLUT2 is also important on cells that have an apical and a basolateral side. Basically, cells that have glucose on one side of the cell that they need to get over onto the other side. Can you think of any cells like that? The small intestine is probably the first one that comes to mind because it needs to get glucose from the gut into the body. But the other equally important one is the proximal tubule cells of the kidney. They need to move all the glucose in your urine back into the body. GLUT2 is used to export glucose from inside the cells to the body's interstitium. But how do you get glucose into the cells in the first place? Hint, it's not a GLUT transporter. All the GLUT transporters are purely for passive diffusion, which is fine because in most cases the cell just takes what it needs, and where there's low glucose concentration, more diffuses in. But when your goal isn't just to get enough glucose, but rather every last little bit, well then you need to kick it up a notch. You could use active transport, but why spend energy to gain energy, right? To solve that problem, nature invented the SGLT channels, which stands for sodium glucose transporter. In a genius move, the cells harness the power of the extracellular sodium gradient to drive glucose into the cell along with a sodium molecule. Pretty slick. The only problem is, you have to pair it with GLUT2 on the opposite side to help glucose escape the cell. Because otherwise you're just going to pump glucose in so fast that the cell will literally explode. Other than bidirectionality, the enzyme kinetics of GLUT2 are pretty special. And for those of you who want to smack your heads against the desk at even the thought of biochemistry, well, you can skip ahead to GLUTs 1 and 3 because this isn't honestly that high yield. The reason I'm presenting it is, I really think it helps you understand why this transporter is where it is in the body. At lower and most physiologic glucose concentrations, GLUT2 transports glucose slowly compared to GLUT4. For the liver, that means letting other tissues have first dibs when supplies are low. But it also has an insulin-independent mechanism for picking up the pace when glucose levels are too high. The GLUT4 transporter maxes out pretty quickly, but 2 has a high capacity for transporting large amounts of glucose. To use the terms you learned in pharmacology, GLUT4 has lower Km, which means higher affinity, but GLUT2 has the higher Vmax. In the liver, this is one of the mechanisms for preventing critical hyperglycemia. If blood glucose starts to go haywire, the liver can keep sucking up glucose faster and faster. In the kidney and small intestine, it means that GLUT2 can rise to the challenge if the SGLT channels are threatening to increase intracellular glucose concentrations to cell-exploding levels. So I explained why the liver, small intestine, and kidney need GLUT2, but the pancreatic beta cells also make use of the bidirectional transporter. And this is a little less intuitive. So why use GLUT2? Because the beta cells need to know when there's a lot of glucose so they can secrete a correspondingly large amount of insulin. Think about it. If they had a low capacity transporter, they'd increase their levels of insulin until about a concentration of 120 milligrams per deciliter, at which point they'd be all, well, I'm about done here. And that's bad news bears. We want our beta cells to be able to modulate insulin levels over a wide range of glucose concentrations. There are a few other important glucose transporters, none of which is regulated by insulin. For starters, these two behemoths, GLUT1 and GLUT3, are very high affinity, high capacity transporters. Now, carrying high levels of these transporters is basically like having access to an all-you-can-eat buffet of glucose, even in times of starvation when glucose is scarce and insulin's bottoming out. So, which cells deserve first dibs on glucose? Well, the brain certainly comes to mind, as does a close extension of the CNS, the eyes. And as you might remember from repro, fetuses also get first dibs on glucose in a pregnant mother. Placentas are chock full of GLUT1 and GLUT3 transporters because fetuses are basically like tiny parasites that hog all of mom's resources to grow. That's why even when mothers get hypoglycemic, it's very hard to make a fetus hypoglycemic. The last type of cell that gets one of these mammoth transporters is kind of surprising. The humble red blood cell. Now, what makes these guys so special that they get an all-access pass to glucose heaven? Remember, RBCs have no mitochondria and can't undergo anything more efficient than anaerobic metabolism of glucose. So they need to chew up a ton of glucose to meet their energy requirements because they're physically incapable of oxidizing fats. The last of the glucose importers is this weirdo called GLUT5, and it's actually a fructose transporter. There aren't too many cells that use fructose, but the small intestines can absorb it and convert it to glucose for the rest of the body, and sperm actually do use it primarily for energy. If you're having trouble remembering these, don't worry, you're not alone. If you have to triage your knowledge, GLUT4 and GLUT2 are the most highly tested, followed by SGLT. Remember that GLUT2 is a two-way street, unlike the other ones, and that it's found in the liver, paired up with SGLT in the small intestines and kidneys and in the beta cells. GLUT4 is insulin dependent, and it's on the muscles and the adipocytes. Alright, my friends, that's a lot of information on insulin, and nearly all of it's important, so I think it's time for a flash quiz. We'll keep this quick. Which glucose transporter is the slowest at low glucose concentrations? Go ahead and pause the video if you need time to think. And the answer is the GLUT2 transporter, found on both the liver and pancreatic beta cells. Thanks for watching, citizens of RX, and if you liked the video, don't forget to give me a thumbs up down below, and as always, comments are more than welcome.